It's our great pleasure to invite three distinguished speakers this afternoon. So our first speaker will be Gade Shumel from Smith School of Business, University of Maryland, and she's going to talk about a very interesting topic: to explain or to predict.
Thank you very much. So I guess thank you for coming to the basement at 5 o'clock. You know, kind of is a weird place to meet. I guess our session is called Business, maybe because some of us are from business schools. But in fact, my topic is not at all limited to business and is talking more about using statistical for developing and advancing science. So the running title for this, the longer title is actually Explanatory versus Predictive Modeling in Scientific Research. And the reason I'm putting in scientific research here is because I could have given this talk in terms of applications and you know, those types of industrial applications. But what I'm going to do today is talk about the angle of using statistical and empirical models for developing science. So I'm talking about scientific research. And the reason that you have this little fish looking right at you, that might be a little scary at this time of day. Does anybody see a theme across the two pictures? Across the two photos? I see something happening in both of them. Newspaper, thank you. Okay. So the newspaper here is being read in the morning to get the news, and here it's being used to wrap fish. And the reason it's up there is just to give you an idea of how I'm thinking of statistical modeling. I'm thinking of statistical models as tools that can be used for different goals, but then you'll need very different qualities. So if you want to read the newspaper in the morning, you want very different qualities, such as having fresh news and having it in a format that you can hold next to your coffee mug. Whereas if you're going to be using it to wrap fish, you don't really care if the news are fresh. You care more about how well the paper absorbs moisture and things like that. So that's the general idea. And I think there's not more than one formula in all of my slides, because what I'm trying to do is not engage you in the technicalities, but sort of come out of all the technicalities that are happening behind the scenes and sort of think about how statistical models are used out there. Now, let me just say a word about where I'm coming from. My undergrad, long time ago, was in psychology and in statistics. And in psychology, I took some courses on research methods, and that's how I saw how statistics was being taught in psychology. Okay? And then later on, I had my degrees are in statistics from the Israel Institute of Technology. Later on, I moved to Carnegie Mellon for 2 years, and I worked there with computer scientists, data miners, and with epidemiologists. I did some work in biosurveillance. And after that, I moved to the University of Maryland, and a lot of collaborations of mine have been with information systems researchers. These are people with training mostly in behavioral science and in economics. And I've done a lot of work in electronic commerce together with these people. And by working with all these different researchers, I've realized something very, very interesting. And that is that statistics is used very, very differently in the social sciences, in engineering, in medicine, and in statistics. So we're all really living in very, very different and sometimes and often parallel worlds. And the topic of this talk, which was to explain or to predict, is really about thinking about an aspect that most statisticians don't even consider, because usually they're not aware of how statistics is used outside. And the other thing is that a lot of non-statisticians don't consider this because they study their statistics courses from statisticians. So let me get into details about what's going on. Here's a short roadmap of the talk. First of all, I'm going to have to do some definitions, because when I say explaining, everybody here understands something different. Social scientists understand one thing, engineers understand a different thing, statisticians, everyone has a different understanding of what explanation is, and I need to define that very clearly. And then I'll explain prediction, I'll define explanation, and I'll define what I mean by model. Model is also another very ambiguous term. After I define those things, I'll give a very, very quick view of how statistical models, and I'm calling them empirical models because I'm including data mining algorithms, anything that you'd be using to analyze data, very briefly in the social sciences, because I think that most of the people here are more familiar with engineering and statistics. Very quick, I'll do that. That will lead me into the question of why is there a difference if we're building statistical models for prediction versus if we're building models for explanation. And I'll try and give an intuitive explanation of why this difference, where this is even coming from. And this is going to lead to my two main points. How does this manifest in practice? One point is going to be that explanatory power and predictive power are totally different things. And you can't infer one from the other. And that's, in fact, what happens in most sciences. My other point is going to be when we talk about building a model, okay, not evaluating a model, but building a model, then when you want to build an explanatory model, statistical model, you'll be doing things very differently than if you're trying to build a predictive model. And the differences are going to arise at every step of the modeling, from how you collect your data, how you analyze it, how you impute it. Everything that you do is going to be different. Okay, so these are going to be my two main points in this talk. At the end, I'll kind of say very quickly, well, what happens if you ignore all this and we just keep doing what we've been doing and science keeps doing what it's doing? And finally, of course, well, what's our role here? Who's at fault? So it's nice to blame someone, right? Okay, so let me start with very clear definitions. And again, you might not agree with these definitions, but these are my working definitions so that when I use these terms, you know what I'm talking about. When I talk about explanation, I'm going to be talking about causal explanation. Okay? So when social scientists are trying to explain a phenomenon, they're interested in a causal theory. If this is going to happen, then that is going to lead to that. Okay? Arrows pointing causality. I'll talk about predicting in a moment. And again, when I'm going to say model, I mean a statistical or empirical model. Again, it can be a data mining algorithm just as well. But this is not a physical model. This is not a theoretical model. This is not a mathematical model. This is a statistical or empirical model. Okay, so here's the definition for explanatory model. I'm going to call a model, a statistical model that is used for the purpose of testing causal theory, an explanatory model. Now you notice that I wrote you proper or not. Well, as a lot of you who've done work with social scientists will recognize that a lot of times a regression model, for instance, will be used for testing causal theory, and causal statements will come out of it. Whether you agree or whether you don't doesn't matter. I'm going to be calling that type of model an explanatory model. Okay? All right. The other definition is predictive model. And when I'm talking about predictive model, I'm talking about an empirical model that's used for the purpose of predicting new records or new scenarios or new observations. In other words, this is practical predictions. This is not scientific predictions where you say if condition A and condition B happen. No, not those hypothetical predictions. This is actual predictions, okay? Numbers or categories or whatever you want it to be. Okay. So now with these two definitions in hand, let me kind of tell you where I think we are. So these are supposed to be two different planets, right? I don't know, men are from Venus and women are from Mars. In my eyes, this is, first of all, again, this is all from my own experience, okay? And thankfully, I've given this talk a bunch of times, and this does stick. I'm not just inventing this. The social sciences live up here. What they're interested in is generating causal theory. Okay? And they're using statistical methods for explanation, for causal explanation. Now, most of the tools that statistics has developed over the years, and if you go and open the top journals in statistics, are inference and based at explanation, although statisticians often shrug when they see, if they see, how their counterparts use it for causal explanation, right? I mean, the mantra, correlation is not causation, and you can't say that. You can't do that. Forget it. That's how these models are being used. Regression models are the most widely used tool in economics for causality. Okay? So this is one planet. Now, as I'm claiming again, statistics methodology has really focused on inference, mostly. On the other hand, you have this world where people are trying to predict, and if you think of machine learning and data mining, really most of the algorithms that are being built there and developed there are geared towards prediction. Okay? So if you ask people, well, what's the difference between statistics and data mining? I guess the most common answer is there's a lot more data than it's data mining. In my view, which is probably very biased by my own craziness here, that's not really the difference. The main difference is that data mining is aimed mostly towards prediction, and that's why they're building algorithms that have to work with that. Whereas statistics was originally built for testing hypotheses and testing theory. Okay? So I think that's where the differences are. And in fact, they're not really competing because they're really trying to achieve different goals. The fact that you can use some of these methods up there, some of those methods down here, great. All right, now here's the cynical part. Here's where the statisticians are most of the time. So we're usually engaged in building models that just describe well, that are compact. We'll use a regression to say, oh, so this is how these things relate. Forget about causality, they relate. Or we build histograms, right? So we're really about describing the world, but we're not really trying to build causal explanations unless we're doing design of experiments. And prediction is a very minor part. I mean, open any textbook in statistics and look at the index under predict. You'll find prediction interval. That's about it. Okay, now from here on, let me just kind of do a really quick word about how statistical modeling is used in the social sciences, okay, for research. So in a nutshell, very, very brief, just a quick one. Now, as I said before, the main usage is for testing causal theory. Here's what a typical article will look like in, I don't know, psychology. I can tell you information systems. I know that literature the best. Here's how it's going to go. You'll have a paper. It will start out with a theoretical causal model. Here's a bunch of causal things, and if these things are going to happen, they're going to cause the person to behave in a certain way. Okay? Few pages about the theoretical model underlying. No data at this point. Next thing that will happen, you'll have a set of causal hypotheses. And again, in information systems, you'll have sets of hypotheses, maybe 6 or 7 sets. If this happens, then that's going to happen. Positive effect. This is going to be negative effect. Okay, just a bunch of set of causal hypotheses with causal words. Everything's intended to be causal. And the next step, this is already a third of the paper is done. The next part is going to be a very important and careful part of operationalizing the concepts. So if you think of concepts in any field, if you want to think of anger, okay, you're going to have to tell me how you're going to measure anger. Is it going to be measuring someone's blood pressure? Is it going to be a survey where they report, how angry they are? There are lots of ways to operationalize these concepts from the theory. And this is a very, very hard task to define how you move from the concepts to the measurements. And it takes a lot of justification in many pages to explain why it's a valid measure. Okay? But remember this is going to be one of the main culprits here. Only then some data and statistical parts come in, and this is where a statistical model will be devised to try and test these causal hypotheses, and inference will classically be used for that purpose. Then you'll get some conclusions in statistical words, right, statistical significance and all that. And finally, this will be wrapped back into the theoretical conclusion, say, okay, hypothesis 1, we were right, hypothesis 2, we were wrong, 3 is right, 4, and say, based on that, here is how we confirmed the theory or rejected some hypothesis or whatever. This is what a typical article will look like in the social sciences. Okay.
One quick question.
Sure.
Why do you put the process part? That is, sometimes something happens from an inherent stochastic process. It can be scientifically verified.
It won't exist here. Because here, the big model is a theoretical underlying causal model. And you don't really need to make any assumptions about a stochastic process that if it is, then it will be folded into the statistical model. But I don't typically see very...
Not upstream.
No. And that's really a difference between statistical papers and a domain type of paper. Because they believe that there's a truth, a reality, which a statistician would say a stochastic process is the reality. It's a different view of what's the reality.
In social science, you're right, but in biological science and physical science, there are a lot of times inherent stochastic model there, which is explained through quantum mechanics or some other process.
Okay, so you're bringing up a good point. They'll sometimes take some kind of let's call it a mathematical model in some way, okay? But then that will, again, just be a way to try and represent the theoretical model in some way. And then a statistical model will be built in front. Okay? So again, my point is there's going to be causality going on here somewhere. Otherwise, they're not moving their science along in the way they're looking at it. So there are two lessons that I learned by doing all these collaborations. My lesson number 1 is whether we like it or not, whether statisticians like it or not, in the social sciences, association-based statistical models, such as regressions, ANOVAs, path models, whatever you want, are used for testing causal theory. And you can shrug and you can say it's wrong. It doesn't matter. This is what happens out there. This is how psychology and sociology and education, this is how things work there. Okay? So, can you just shrug it off? Well, not really. Because the justification for drawing causation from a correlation model is saying our theory has all the causality built in. We don't need to infer the causality from the data. We have the causality, it's well known, it's given. All we need the statistical model is for quantifying the effects. Okay? So that there is a justification. They're not just doing it wrong. Okay. So this is one lesson. My second lesson was about prediction. So I asked, okay, fine. This is how they're using statistical models, but do they ever use it for prediction? Practical prediction. Question.
I'm sorry to interrupt, but
Yeah.
Have you ever asked your collaborators why they don't work within the framework of the Rubin causal model?
Let's leave the questions to, believe me, let me go through the whole
Okay.
thing. You'll have a lot more rage towards the end. Okay. So what about prediction? So what we did was me and a colleague of mine in information systems went into their top journals, did a big search across 10 years, full text articles and whatever, looked for anything that had a word similar to predict, forecast, predicting, anything of that ilk, okay? We found very few articles that had something of that ilk after cleaning out articles that said predictor, okay? Let me kind of change it. Eh? All right, very few articles doing prediction. And in fact, if you talk to anyone in the social sciences and ask them, well, if you build a paper that's about prediction, are you going to be able to publish it? And they'll laugh. Okay, it's very hard to publish a paper like that. So my second lesson was that in social sciences, empirical prediction is actually considered unacademic. You talk to people and you say, why is it hard to publish? Well, it's just an application. It's for industry. We don't need to predict. And that was the most shocking part to me is they don't think that prediction is important. They'll say it's for applications. Yes, we agree. Well, I mean, it's not really fair to blame them because even within the statistics community, there are a lot of people who think that prediction is not academic. Emmanuel Parson, he's pretty well known, wrote in response to a well-known article by Leo Bryman in 2001. He says, the two goals in analyzing data I prefer to describe as management and science. Management seeks profit and science seeks truth. And at some point, someone said, well, that's not what he meant, prediction and explanation. So I emailed him and I said, dear Emmanuel, is this what you meant? He said, yeah, that's exactly what I meant. So there are a lot of people who consider prediction not to be a scientific academic endeavor. Okay? All right. These are just facts. I haven't made, right? Okay. You can see where my opinion is coming in. So here's my opinion, my personal, humble opinion. You can't really advance science if you're not doing both. You have to have causal model testing, but you also have to have prediction alongside. And if you don't have these hand in hand, you're stuck in going in circles. Now, again, I could kind of be controversial and say, well, when did the greatest theory come out of psychology, sociology lately? Huh? Well, because there's not a lot of prediction going on there. But before that, let me try and convince whoever here thinks that prediction is not scientific, why it is scientific. Utility aside, okay? As I said, utility is important. Everybody agrees on that. If you can predict the next outbreak of avian flu, useful. But we're not talking about that. We're talking about developing scientific theories. Number one, relevance. How do you test that your theories are relevant to the world? You can test and show p-values and do whatever you want for the rest of your life, but you'll never actually test the relevancy of your theories. You have two competing theories. How do you compare between them? Maybe they both have very compelling evidence over time. So number one is predictive accuracy and predictive modeling are really useful for assessing the relevance of causal theoretical models. So it's the way to test them. Reality check. Number two, lots of fields kind of died on theory when we moved online. I work in online auctions. When you move from offline auctions to online auctions, game theory crumbles. If you want to predict what's going to be the final price, and then you have these nice equations in game theory, you tell me the number of bidders, it doesn't work. You go online, there are a lot of other effects going on. People are cheating, there's heating up, emotional. There's all kinds of things that happen there. Think about all these sciences. I mean, I think it touches every science. When things moved online and you move into a new era, a lot of the old theory crumbles. How do you generate new theory? Sometimes you just need to see what's going on. And predictive models are very good at finding out new theory. So this is, again, kind of going between them. You find some new stuff, and then you say, OK, let's understand why it's happening. Let's build explanatory models. And then you test them, and then you do a reality check, and so on and so forth. And the last point, the last principle of why prediction is very academic and very scientific is because it allows us to assess whether something's even predictable. I won't even say financial meltdown. Oops, I said it. Okay? I mean, if we're building all these beautiful models, but we're trying to predict something that's unpredictable, then we need to know it ahead of time. And that's fine. Maybe you build a causal model that is not, it can't predict right now. Think of string theory in physics. It explains beautifully everything, but because of technology, we can't use it we can't verify predictions yet. Okay? But to say that is very, very useful. Okay, so I hope I convince you that prediction is a scientific endeavor. Assuming that I convince you, let me get to the main issue. Why are statistical explanatory models going to be different, as I said before, from predictive models? Why can't you just build a good statistical model and it will explain well and predict well? And that's the notion that most people have, is if I build a good model, it should be good for both of them. All right, let me just start and say I didn't invent anything, okay? I just went back and started thinking about things. And it's a whole interesting story of how I got to this, but I'll just kind of go back to philosophy of science, okay? 1940s, Early on in philosophy of science, people thought that explanation and prediction are the same. This is not data. This is just logical structures. Hempel and Oppenheim in 1948 said explanation and prediction have the same logical structure. Slowly, there was started a debate, and for instance, in 1959, Helmer and Rescher wrote, it becomes pertinent to investigate the possibilities of predictive procedures autonomous of those used for explanation. Okay? And finally, 10 years after this, in a well-known book called Theory Building by Duman, he writes, theories of social and human behavior address themselves to two distinct goals of science, prediction and understanding. Now again, this has nothing to do with statistical or empirical models or data.
You have to go back a little bit. You have to go back to at least Jeffrey's.
I can, but I have 30 minutes.
Right?
No, okay.
Right? I mean, you have.
We can go even further back. Fine. All I'm saying is, I did say.
But they're talking in the context of statistics already. Both
Okay.
And Jeffrey.
Okay, we'll talk about Jeff. We can do that offline. But yes, I've been there. Okay. So now this stuff is coming not related to statistical modeling. Okay. I'm talking about explanation as causal explanation, and I'm talking about prediction as practical prediction. So what I'm saying is, let's take this stuff and translate it into statistics, and let's see what happens. Okay, so I'm going to do something a little weird here. I'm going to try and give you an example of why things are going to be different in statistics. What we see here is a famous painting by Van Gogh, right? And he painted this while he was in an asylum across from this little village. You can see that little village down there, very Van Gogh style. And let's assume that I am now, that this village is gone, and all I have is the painting, and I'm a historian, or an architect, or historian, architect, or whatever, and I'm trying to learn about what this village looked like based on the evidence that I have on this painting. What I would have wanted this painting ideally to do is to be as the most realistic, right, image of what this village is. I would have wanted Van Gogh to really get the details right and everything correct. Yeah? So I want the painting, think of the painting as the data, to be as close as possible to reality. Think of that as a theoretical model, as you want. Now let's think of someone else. Now I'm no longer the historian. Now I'm a museum restorer. And this horrible patch turns up on this ugly, right, and it's really ugly on this beautiful painting. And what I need to do is to restore this area and make it look, right, as if it doesn't exist. Do I really care what the village looks like, or do I care more about brush strokes and paints and the Van Gogh style? There's just a talk by the Google guy, right, talking about image. So we don't really care about the truth behind the scenes. What we care about is the data. In other words, in prediction, we're operating at the level of the data, of the measurements. Whereas in causal explanation, we're not operating at the level of the data. We're using the data to operate at the level of the truth. So we're trying to match the truth to the theory, whereas here we don't really care about that theory that much. And think of correlations, right? This is close to that and close to that. All right, so that's just an idea of this concept operationalization and what it causes, this disparity between what you're trying to talk about and what you're measuring in explanatory models, whereas in prediction that doesn't exist. Okay, now I shouldn't say that none of this has gone into statistics. There's one area in statistics that's very actively separating explanation and prediction, and that is model selection. If you've done anything in this field, there's tons of things, and here's just one quote. The goal of finding models that are predictively accurate differs from the goal of finding models that are true, and this is a quote from Richard Burke's book, Statistical Learning from Regression Perspective, very nice book. But there's a ton of these, and people recognize that if you're using AIC or BIC or doing it this way or the other, you're not going to get the same model if you're trying to get the right underlying model or if you're trying to predict. Okay? There's a whole lot of stuff in this field. But here's my claim. The difference between explanation and prediction is much more vast than in the model selection. If you've gotten to model selection, you've kind of missed out on a lot of action. Everything is going to be different from the point in time where you actually design your study and collect the data and clean the data and explore the data. And this is only when you hit the model selection part. So what I'm saying is, let's take the separation and look at it through the statistical eyes from the very beginning to the very end of how we actually go about doing an analysis. Okay? So my two main points again are going to be, one, that explanatory power is not predictive power. They're different dimensions, and you can't infer one from the other. And the other is that building an explanatory model is different, so different in every step than building a predictive model, that at the end of the day, you'll never get one model that is the best in both, unless it's a toy, silly example with not interesting signals, data, and noise, okay? In other words, if you're after explanation, you really have to go and slowly build your model according to a certain path, whereas if you're after prediction, You want to go down the predictive path. Okay, so point number one is actually pretty easy. Especially with statisticians, it's easy, although with social scientists, it is not easy. And the main issue is that most of the types of metrics that people use that are in sample, like classically R squared, and you'll see tons of articles that say our R squared is this high, therefore our model can predict well. That's the biggest thing if you look in the papers anywhere. They're just wrong, because R squared is not measuring predictive accuracy. It's measuring strength of fit within your own data. It's very biased towards you. And again, the machine learning people really know about this difference between in-sample and statisticians. I mean, we do cross-validation, right, because of this issue. But that is one big difference between in-sample and out-sample. The other issue is going to be, if you're trying to explain, you really care about interpretation. So you want to make sure that you're building models that you can interpret. That's why regression is so popular, right? You can interpret a unit increase in this causes blah, blah, blah. You're using statistical significance to talk about inferring into the population, and you're doing a lot of goodness of fit, residual analysis, and all that. If you're trying to predict, this doesn't matter. P-values, not very important. And actually, it turns out that sometimes, if you throw out some significant stuff, you get better prediction. Right? I mean, that's what we do with shrinkage models and stuff like that. And there are papers that show that you can choose the wrong model, and it will do better than the right model in terms of prediction. So that's not new either. And finally, again, when we're doing inference and explanatory stuff, we're really worried about type 1 and 2 errors, alphas and betas. We couldn't care less about that stuff when we're doing prediction. All we care about is not to overfit, because then you can't really get any model accuracy, right? Predictive accuracy. So this is just in terms of how things are different. And again, we can think of extremes. I love thinking of extremes. They really kind of give perspective. If you think of these two different axes, predictive and explanatory power, then remember when we thought the world was kind of going around us and it was the wrong model, turns out to be? This has very good predictive power, and until GPS, this is what people used to navigate on ships and at night and whatever, until recently. Why? They knew it was the wrong model, but it produces very good predictions. Whereas if you think of a model that has very low predictive power, but very high explanatory power, remember this guy? Someone here had a t-shirt where the next one's like a Bayesian, but yeah. So you can't really predict what the next guy's going to look like, yeah? But it has very high explanatory power. Now, most of the theories that we're seeing in different places are not, as dramatic as this, but you want to know where they are in this space. An explanatory model doesn't have to be all the way up there, but you want to see where it is so that you can compare it with other theories, so that you can see maybe predictive models, how well they're doing, what's the gap, how far can we get. Okay, so the thing is, if people would start reporting both, and not just this, in explanatory tasks, science would at least sort of, get a little challenge there. All right, next point is building an explanatory model is different than building a predictive model, and this is where I have to really run. Okay, gotcha. Okay, I'll just say a word that in the Netflix prize that a lot of you probably have already heard of in lots of other talks, it turns out that adding a lot of other attributes about the movies, which was one of the first things that competitors did, they went and looked at every movie and grabbed a lot of information about it from other websites. Turns out that actually made predictions worse. Now, if you're trying to explain why a certain user rated a certain movie a certain rating, and you excluded any other information about the movie or about the person, that would be a really bad explanatory model, right? There's no causal stuff going on. So this is a classic thing where prediction really led to something else, and I won't do the quote. You can read the bell it all online. But let me sort of make a few nuggets, a few points. If you think of the statistical process of modeling, and I just built it very generally from goal definition, collection, preparation, exploration, choosing variables and methods, all the way to the end, everything's going to be different. And I'll give you just a few points. And again, there's 2 papers there that you can see all the details. I'm just designing the study. Should I do it observational or experimental? Well, if you're trying to explain, then obviously experimental is better if you can afford it, right? Because then you can really kind of infer causality. How about if I'm trying to predict? Is a lab experiment always better than just going and getting some dirty field data? Not necessarily. Sometimes the lab data are too clean to actually be useful for prediction. So what I'm saying is the criteria that you'd kind of think about to choose one versus the other would be very different. How about primary or secondary data? Primary data are those that you collect especially for the task. Secondary data means you just took some other data, secondary data or something, or census data or whatever. What would you choose? Well, there are different criteria to choosing one versus the other, but they would be different if you're trying to build a predictive model versus you're trying to build an explanatory model. I can give you lots of other examples. Which instrument are you going to use? If you're trying to explain and you're doing a survey, right, they delve on the reliability and validity of the questions. Are they really measuring what they're supposed to measure, etc. But if you're trying to build a predictive model, you fill in a survey and it gives you the next web page accordingly, You don't really care about whether they're lying to you or not. You just care whether your model is predicting correctly their outcome. Yeah? So the instrument would be different, and how much data would be different, because it depends on the algorithm and whether you need a holdout set. And even the design, whether you're going to do a hierarchical design and how you're going to sample within the different schools, few students across or lots of students in one, it turns out to be the opposite strategy if you need to predict or to explain. And again, there are papers showing all these little nuggets, but no one kind of put the dots together. This is very interesting. Missing values are always there, right? There's the Rubin thing of missing at random, missing completely at random. That's the classic thing for explanation. Turns out that for prediction, those are not the right criteria to look at. And Jeff Simanoff has a very nice paper that just came out showing that the most important thing about missingness is whether the missingness is predictive of the outcome or not. So if all the firms are not some firms are not filling out a certain number, maybe that's the most important part, and you really shouldn't impute that, yeah, because maybe they're the fraudulent ones that you're looking for. Another very interesting issue that relates to imputation is Foster Provost from NYU, data miner, shows that he says, you guys have all these fancy things for imputation. Why didn't you think about a very simple way to do it? These persons don't have income, these people don't have age. Just build a bunch of models, some models without age, some models, right? And then a new person comes in, doesn't have age, use this model. Fine. Very nice for prediction, very bad for explanation. You can't build a bunch of models, right? There's theory there that's guiding what goes in and what goes out, et cetera, et cetera, et cetera. Again, I won't move too fast. I'll have to move fast because there are lots of things that, again, nuggets that you do in prediction, but in explanation you really can't go free form, and that's not how people explore the data in explanation. Variables, choice of variables is it's the obvious thing basically. Whereas in explanation, theory guides which variables should go in. In prediction, it's all about correlations and association, right? If I can predict tomorrow's weather from today, perfect. Very bad explanatory model, very nice predictive model, right? Okay, here's the very important one, ex post availability. If you're building a predictive model, you need the predictors to be available at the time of prediction. If you're trying to predict the price of an auction on eBay, and game theory tells you need to plug in the number of bidders, well, I don't know the number of bidders until the auction closes. So that might lead to a great explanatory model with a number of bidders as a predictor, but I can't use it in a predictive model. End of story, different model, right? Not the best predictor, not the best. Okay, and it can keep going on. Multicollinearity is not a big deal with prediction, and identifiability is a different story. And I'll just mention that this bias variance trade-off that machine learners love, that is actually very important, and that really leads to what you used for explanation versus prediction, which method you'd even consider. Okay, I'm going to fly around and move out of here just so that you can see that there's a lot of different things going on here. And I'll just say one last point here, and that is the fact that we're not recognizing any of this stuff means that, one, prediction is really underappreciated in lots of sciences. On the other hand, you go to some other areas and they'll say we only do prediction. Every time we fire, how does it go? Every time I fire a linguist, the predictive accuracy goes up. Okay, so some sciences do prediction, some sciences do explanation and don't consider prediction. Definitely the distinction is totally blurred right now, and what we're seeing is a lot of inappropriate modeling. To close with a final thing is, while the value of scientific prediction is beyond question, the inexact sciences do not have the use of predictive expertise well at hand. This was 1959, nothing really changed. All right, I'm going to close with this, and sorry for running a couple minutes late.